Okay, so we're asked to prove the sum formula for a GP. Okay, so this is the formula, of course, so we've got to be ready to be able to prove it. So first of all, if we write this statement, let Sn be the sum of the first n terms of a GP, okay, geometric progression. Okay, well, what will that look like? Well, Sn, of course, will be, well, the first term is A, isn't it? Yeah. To get the second term, I've got to add, no, not add, I've got to times it, haven't I, by the ratio R. So AR. And to get the third term, I have to do AR squared, don't I? Okay. And then to get the fourth term, maybe times it by R again, to be AR cubed, and so on. So we keep on going like this until we get to the nth term, okay, which would be AR to the power n minus 1. Okay. Well, what we can do then is, okay, this is a bit different to the AP proof of summation, but what we do in the next line is we write the whole thing out again, but this time we times it by R. So I'm going to times Sn by R, okay, so times it by the common ratio. So in other words, I'm timesing everything here by R, okay, because I've got now I've got RSn. So if I times A by R, I'll get AR, won't I? Okay, so that first term times by R, I get AR. So what I'm going to do, slightly clever, and instead of writing it here, we're going to write it underneath here. Okay, so it sort of lines up for us. So times that by R, I get AR. Times that by R, I get AR squared. So just write it underneath here. Times that by R, I get AR cubed, which will be in here, this dot 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 thing going on, okay, right? And then what you need to appreciate is, this is AR to the n minus 1, yeah, okay? Well, the term before it will be AR to the power n minus 2, and because I'm timesing that by R, I end up with AR to the n minus 1, okay? And I write it underneath that one. And then if I times that by R, okay, I get AR to the power n, okay, right, times that by R, you're adding a 1 onto this, so it becomes just AR to the power n. So what we do then is we take away, right, so I'm going to subtract, I'm going to do this, take away this, so Sn, take away Rsn, and what happens is here, of course, then, because they're all lined up, you've got A here, take away this term, well, there's nothing there, isn't it, okay, so it'll be A, take away 0, which is A, AR take away AR is 0. AR squared take away AR squared is 0. You've got AR cubed take away AR cubed is 0. AR to the power 4 take away AR to the power 4 is 0. AR to the power 5 take away AR to the power 5 is 0, and so on and so on. We come to this last term then. Take away this term here is 0. And we write at the end then, well, you've got nothing here, take away this. So nothing, take away this. It's quite simply be minus AR to the power n. Okay, so that's what you're left with. And what we can do from here then is you look on the left hand side, okay, and you can hopefully appreciate that Sn is in both terms here. So we can factorize out Sn. So Sn times 1 gives me Sn. Sn times minus R gives me minus Rsn. On the right hand side, do we notice then A is a common factor? So bracket A times 1 gives me A times then minus R to the power n gives me AR to the power n. Take this over to the side and you're left with what we want, okay, the summation formula. So we've got the Sn formula there, but we're not quite done, because it says then, given that R is less than 1, write down the sum to infinity of the series. Now, if R is less than 1, okay, it's important to realize then that the sum to infinity exists, okay? It only exists if the size of R is less than 1. If the ratio is greater than 1 or even equal to 1 or greater, it doesn't exist. Okay, so what you've got to do is focus on this here. This is your focus, okay? So you say, look, as n gets big, okay? So let's put it in sort of layman's terms to start with. As n gets big, really big, R to the n, what will happen to it? Now think about it, okay? R is less than 1, okay? so it's a decimal less than 1. If you put a decimal less than 1 to a power, okay, it gets smaller and smaller. Okay, so if r was, for instance, 0.1, and you put 0.1 to the power 10, it's like super small. So as n gets big and bigger and bigger, Rn gets smaller. Okay, and closer to 0. And then in technical terms, okay, we need to think then as n gets to infinity, okay, super big, never ending, okay, Rn will literally go towards 0, okay. And that's what will happen. Rn will tend towards 0 as n tends towards infinity. So in other words, in our Sn formula, well, if n's going to infinity, we've got S infinity. A then, bracket, 1 minus, well, r to the power n is 0. Okay. On the bottom then you've got 1 minus r. And then it just comes out then, as we know it in the formula book, as A over 1 minus r.